But let's go ahead and dive into the lecture here. I always like to take the pause and make sure that that's being recorded before I get into it all the way. But this is kind of growing on what you have seen so far in that lab that you've just done, right? Talking about what goes on with what we will soon establish as electromagnets, right? And dealing with a lot of loops. So here's kind of a review slide of some of the stuff that we have seen so far, right? We remember that there's two-ish Biot-Savart laws, right? One is for a single particle, a single charged particle, I should say, moving with some velocity. It creates a magnetic field. And if you have many moving charges all at once, then the equation on the right side does a little bit better. But we also found that if I were to have a wire with current and it's infinitely long and not really curvy or anything else like that, it's mostly a straight wire, then we've got a simplified form of this equation that we could use sometimes that might be useful, right? Just like what we have seen with an infinite rod, even if you don't have an infinitely long rod, a sufficiently long rod, or a sufficiently long wire in this case, you get a pretty close answer, right? And 99.5% of the way there is most of the time good enough for us. So what would happen if we took this wire and we curled it into a circle, right? And we have some current going through this, some sort of circuit like this. Well, what we would find is that at every point along the axis, we're the same distance away from that wire, right? Which makes that lowercase r that we would see in this equation a little bit easier to deal with. Right, but I'm not going to walk through this derivation completely. It's not the worst derivation in the world, but it is done in the text as an example. So we're just going to kind of pull that result for now, right? But this is what we get if we were to have a loop of current in the magnetic field because of that. And this equation should look kind of familiar. Not exactly familiar, but a little bit because, well, let's look at it real quick. What's going on there? We've got something creating the magnetic field on top, some moving charge, over z squared plus r squared to the 3/2 power. And that should look very similar to what we had found the last time when we were doing this with electricity and the electric field from a ring of charge rather than a ring of current, right? They look very similar because, again, they're the same force. So what you should have also found from doing some of this stuff is what you'll notice is that there is another right-hand rule. And it's the right-hand rule that if I have a loop of current, then if I curl my fingers in the direction of the current. So try this with me real quick. If we're doing this thing from the perspective of the screen, so it's wrapping around kind of like this, then my thumb would be pointing in the direction of the magnetic field. That would tell me my thumb is the north side of the magnetic field. So it's a really useful thing, right? The right-hand rule can be used in a lot of different ways, but it's essentially saying that anytime I'm looking at cross products and things like that, it's this relationship between the three fingers that really tells us what direction things should be going. It's very useful to have. So I want to try this real quick. Let's imagine that we have some sort of loop of charge, and we measure the strength of the magnetic field right at the middle of this loop. How far away from the middle of the loop do we have to get for the field strength to be halved? And we want to answer this because we don't have any real numbers in here. We want some multiple of the radius capital R. Okay, so let's start taking a look here. And I'm going to steal this picture real quick, just so we've got some sort of, whoops, that's not the right thing to click. Just so we've got some sort of visual aid to help us kind of picture what we're looking at here. Could I please get the, there we are. Okay. A series of misclicks. But anyways, so let's shrink this thing down a little bit. We don't need it to be massive. I'm not going to draw on this thing too much. But as we're starting with this thing, we want to find what distance, where does that dot have to be so that we've got half of the magnetic field strength as we do right here in the middle. So the first thing that I actually need to do is I need to find out how much field strength we've got right in the middle. So I'm going to go back and I'm going to steal this equation real quick, right? We know B of z is equal to mu naught over 2. And I always screw this up, so bear with me while I act a little bit slow with this thing. Or let me do this in black, actually. B of z for any sort of point would be mu naught over 2 I r squared over z squared plus r squared all to the 3/2 power. So if we're looking specifically at a red dot, that's nice and easy to deal with because we can just take z is equal to 0, right? That's how far away we are from the center, 0. We're at the center. So let's call this, we'll just do this as the red B, or maybe B naught, for B right in the middle. So this will be mu naught over 2 I r squared. Then what I've got down here is now just r squared to the 3/2 power. That's going to simplify. I know we don't often deal with fraction powers like this, but it's not too bad. So r squared to the 3/2 power. The 2's cancel out, the 3 gets left behind. So I've got mu naught over 2 times I times r squared divided by r cubed is what we've got there now. Simplify to the very end. B naught is equal to mu naught times I divided by 2 capital R. Okay, so now we want to find what is that magnetic field at this point out here, right? Where do we find that point? How do we solve out for this thing so that we've got it set? The first thing I'm going to need to do is I'm going to say, okay, well now my blue B is going to be equal to 1/2 B naught. So this does have some sort of z component, so I'm going to need to write all of this equation out. So mu naught over 2 I r squared divided by z squared plus r squared to the 3/2 is equal to, I'm just going to move the 2 on the bottom right there. So mu naught I over 4r. Let's cancel out some of these things that we don't actually need. Mu naught, that can get out. I, that can get out. Now, remember here that we're solving out for z, which is a little bit nasty. And also, I need to try and make sure my handwriting's not so good today. So I need to try and make sure that my 2's look quite a bit different than my z's. Okay, but what I'm going to do here is I'm going to try and move some of these things over to the other side. So let's simplify this to what we've got right here. Let's move the 2 to the other side. And let's move the r squared to the other side. So what we end up with is 1 over 2r cubed. Okay, this is kind of difficult to solve. So the first thing I'm going to do is I'm going to flip it all, take the inverse of both sides. That'll make it a little bit easier to deal with at least. And then after that, I'm going to take everything to the 2/3 power. So something to the 3/2 power and then taken to the 2/3 power, those cancel each other out. But the right side is going to look a little bit different. So I'm going to be left with z squared plus r squared over on the left-hand side. On the other side, I'm going to have 2 to the 2/3 power and then r cubed to the 2/3 power, just like what we had before. That's going to come out as r squared. Now, move the r to the other side, pull some things out as we see them. Z squared is equal to r squared times 2 to the 2/3 minus 1. So now we just need to take a square root of each side, and what we should find at the very end here is that to get half of the magnetic field, we need to have 0.766 of r. And there we have it. Why the first z is equal to 0? Because the question is asking us for the field strength half at the center of the loop. So the first value that we're actually talking about here is right at the center when z is equal to 0. So, as I've talked about a little bit, but I'm going to kind of expand upon now, magnets don't ever come in monopoles, right? That's one of the big sticking points about these things. We said no magnetic monopoles, always magnetic dipoles. And when we're talking about permanent magnets, or the magnets that you might be used to using, right? Cartoon magnets, everything else, when we think of magnet, it's this thing over on the right, where it's got a north end and it's got a south end, and the magnetic field goes and loops from that. But we can do the exact same thing using current instead, just with this same shape that we are seeing here. Whenever we've got some sort of current loop, well, it creates a really similar looking field, right? It's pretty much identical, actually, to the point that we even still have our same north and south. We still have the same loops going around. Everything looks exactly the same. In the direction, we can find that, again, using the right-hand rule. If our fingers curl in the direction of the current, we can find what direction the magnetic field should be going. So this is kind of a useful thing, right? And that's the right-hand rule that we're after here. But we can use this for all sorts of different things. You don't always have to have a permanent magnet. And in fact, I think I've talked about this. The strongest magnets in the world are not permanent magnets. They're electromagnets, just like this current loop. So, for all of these things, right, all of these, whether it's an electromagnet, whether it's a permanent magnet, whatever it is, they're both acting as magnetic dipoles. And we might remember, dipole things have dipole moments. So we are defining this new value as our magnetic dipole moment, where the magnetic dipole moment, if we had a loop of current, would be equal to the cross-sectional area, or the area inside of the loop, times the current going through the loop, right? And so area, we're talking this whole thing right here. That's the area that we're talking about. So most of the time, it's going to be a pi r squared. But then the magnetic field, because of some sort of current loop, or because of the dipole moment of some current loop, is going to simplify to this. Take a look at this real quick. This will be strikingly similar to what we just found right here, right? What's the big difference, though? What got eliminated? Does anybody see that? What's the difference between these two? What approximation might we be making? It's not just that IR is gone, because IR is actually kind of contained within this dipole moment. Right? It's technically in there because A is a pi r squared, and then it's multiplied by I, so that's still there. But the big difference is that we're assuming here that Z is much larger than R. If Z is much, much larger than R, then we go back to this thing. If this cancels out, we've got Z squared to the 3/2 power. That would give us a Z cubed. And then the IR squared gets kind of tucked away inside of our dipole moment. So this is still along the axis, right? But it does give us a kind of rough quantity for the magnetic field around a dipole, so long as we're talking about a pretty small loop. So, for example, let's talk about a very common magnetic dipole, one that you probably don't think about very often, but is certainly there all the time. The Earth. The Earth has a very large dipole moment, right? 8 times 10 to the 22nd amps meter squared. So, and you can find this, but let's calculate it. What is the magnetic field strength on the surface of Earth measured at the Earth's north magnetic pole, which is actually the South Pole as we know it? And then let's say astronauts or some billionaire that has an electric car company wants to colonize an Earth-like planet, for example, maybe Mars. But the magnetic field on that planet is not strong enough. If we were to make one really big loop all the way around the planet, how much current would you need to recreate the same magnetic field as we see on Earth? Go ahead and assume that it's the same radius. Like I say Mars because that's a common example, but I'll talk about that in a minute. Just use Earth's radius for this. All right, so let's go ahead and start taking a look here. So, and there's some cool stuff in this one, right? This is actually a really neat kind of problem. As we're looking at this thing, we're talking about the North Pole. We don't need to worry about what's going on the sides or anything else like that, because the Earth's magnetic field is actually quite strange, mostly because of how it's formed and the other stuff that gets in the way, and we don't completely understand it, but without digging there and taking a look, it's kind of hard to. So, let's take this equation, though, right? And we've got to keep track of which mu is which. Let's give ourselves a little bit of space here. So we're looking in the circumstance where we have a dipole moment of 8 times 10 to the 22nd. Not a small dipole moment, but we know that the magnetic field from any sort of dipole would be mu naught over 2, mu over z cubed, and I'm forgetting something. What am I forgetting? Mu naught over 4 pi. Which we can simplify if we really wanted to. I'm getting myself mixed up with some of the other ones here. Mu naught over 4 pi, which you guys have caught on to at this point. We can just say that right there is 10 to the negative 7th times 2 mu over z cubed. So all we really need to do is plug in what is the radius of the Earth, and that's a value that we could have found off of our classic constant sheet. So the radius of Earth, if we wanted to plug that in, is 6.37 times 10 to the 6th meters. Right, and if you measure it somewhere slightly different, maybe that's a little bit different, but that's about right. So we take that value, we plug it in. We can say, well, we're not measuring some sort of random z, we're measuring the radius from the radius of the Earth. Plug all of our numbers in. What do we find? Something that's actually not super large. When I plug in all of these values together, I actually find 6.19 times 10 to the negative 5th Tesla. Which is not, I guess, the smallest amount in the world, but it isn't massive. Despite the fact that we have this massive thing, we are still, 10 to the 6th meters away from the source of that thing, so the magnetic field is not going to be exceptionally strong. But this kind of gives an idea of maybe what some of the field strength of different magnets we would have are. I think I said, don't quote me on a value where I said that fridge magnets, for example, would be on the order of microtesla. Which, maybe I was a little bit lower than I should have been, but it's still kind of a relative value, what it takes to stick on that. If you were watching Dr. Alexander go through that lab, you would have also seen that compasses, very light things that are supposed to have not a lot of friction going on with them, they do feel that pull from the magnetic field. It's just when you bring an external magnet close, then it starts to take over a little bit more. Right, so we expect a lot of our magnets to be on that kind of order, maybe into millitesla and everything else, but this is actually enough. Because as it turns out, this value right here and what's going on with this, this is actually what protects our atmosphere from getting quite literally blown away. So the reason that Mars has such a very, very thin atmosphere, it does have an atmosphere, but it's very, very, very thin. It's not habitable for humans or much life at all, for that matter. But the big reason for that is actually because that doesn't have a strong magnetic field. And not having a strong magnetic field, the Earth's magnetic field, as it wraps around, there are constantly particles being emitted by the sun. So because the sun is such a high temperature, even though it has all of this gravitational pull and everything else, there are still particles that get constantly ejected from it, right? We call that solar wind. And there's protons and neutrons and electrons and all sorts of other types of particles from solar flares, or just high energy particles get excited and fly off. But those high energy particles are quite dangerous for a number of reasons, right? High energy ionized particles are typically quite dangerous for a few different things. But what this would normally do is what's happened on Mars. These high energy particles come in, they collide with molecules that are in the atmosphere, and they kind of blast them out. right? And it takes something with it and it carries it away from the planet's pull. In the case of Earth, because we have this magnetic field, we're going to get into this quite soon here, but magnetic fields exert forces on moving charges. Just as moving charges create magnetic fields exert force on moving charges. So when we have these charged particles, they are going to be essentially deflected away towards the north and the south pole of the Earth. So something coming straight at the Earth is going to kind of curve up towards the top. And what happens then is that it does still collide with some of our atmosphere, but only in the very upper reaches of the atmosphere. And those high energy collisions produce a lot of light, and that's actually the reason that we've got stuff like the Northern Lights, Aurora Borealis, right? That's the result of particles from the sun colliding with upper atmosphere particles from Earth because they've been deflected by Earth's magnetic field. So even if we didn't have a magnetic field, we would probably still see many of those. Maybe, well, not as many, right? Because it's deflecting a lot towards that specific area. We wouldn't see as many of those particles, but we would still see a fair few. And then depending on how the Earth goes, sometimes they rotate around a little bit and stuff like that. I don't know which pole has more light. I think it's Earth's north pole that has more. I don't entirely know on that one, though, because I think the difference is it depending on the sign of the charge, it goes in different ways. So protons are going to go to one place, electrons are going to go to the other place. Let me think about this real quick. I'm trying to remember which way it should go. What direction they should be deflected. But I think all of your positive charges are going to go one way. All of your negative charges are going to go another way because the force reverses for those two. So I would imagine it's where the protons are going because that's higher energy, more mass, would probably have more light. But anyways, the reason I bring this up is because, for one, that's why the magnetic field is so nice. But also why we kind of run into an issue when we're talking about like stuff like colonizing Mars. You can't just get an atmosphere on Mars, or a stronger atmosphere at least, because the sun's just going to kind of strip it away again. So there needs to be some sort of effort there to actually have a magnetic field that would help deflect away those high energy charged particles, just like Earth has. So we might have first imagined this to say, okay, well, what if we wanted to try and create the same magnetic field, but using a big coil, a big wire? We don't actually have to match this exact magnetic field, or at least in the arithmetic here. What we can instead do is we can say, hey, if we had the same dipole moment, we would have the same field, right? It's the dipole moment that creates the field. So that is to say, if mu is equal to 8 times 10 to the 22nd, and I times A, where A is actually just pi r squared, solve out for I. And what we find, the current necessary to make this happen would actually be 6.276 times 10 to the 8th amps. Which, if you're looking for our Canvas answer here, that is 627.6 mega amps. Which is not a small amount of current by any measure. That's a lot of current. So, how could we do this? What clever tricks do you think we could actually come up with to make a dipole moment like this, to make a magnetic field like this, and still have it be sustainable or reasonable to run in any sort of fashion? You would certainly have to have high voltage. But one of the issues that we run into with this is we're going to find out pretty soon here, in looking at some of these other wires, big wires, any wire with a lot of current gets really hot. And the hotter it gets, the more likely it is to melt or destroy things around it, the worse it is at being a conductor. There's a lot of issues. Pretty quickly, there's a lot of issues. So what other steps might we be able to take Superconductors, maybe, but you would have to have a planet's circumference worth of superconductors. And because superconductors are still not quite good enough to run at room temperature per se, you would have to have active cooling on that entire thing to keep it at superconducting temperatures. And even then, superconductors technically do have some sort of resistance. And I think even a current like this might be too much for them. There's a limit. At a certain point, stuff gets a little bit crazy. But it would be a step in the right direction, right? It would be certainly something that we would have to do. But I'm looking for one thing in particular. What other kind of ingenious idea? There's one. What if we didn't make it one wire? What if it was 50? What if it was 60,000 wires? Then we wouldn't need to have all of that current going through one wire because we would have 60,000 times the dipole moment, and then we could recreate that with a lower current. And this is a very useful trick, actually. This is why oftentimes you'll see a bunch of different coils with a lot of smaller wires rather than larger wires. Because while the larger wires can deal with more current a little bit more easily, the smaller wires, you can stack them a lot closer together and you can oftentimes recreate these dipole moments in a really massive fashion with the same amount of space. And this is something that I've got a little bit of experience with because in my lab, back when I was doing experimental research, we ran into this issue where the magnetic field affecting our atoms was very, very detrimental. We actually spent a fair amount of time every single day trying to align everything just perfect, and we had essentially a cage of coils around our main experiment where all of these constantly had some current going through them to try and cut out the Earth's magnetic field. It was very important that the Earth's magnetic field was not there. We had a magnetic field, but it was only our own. The Earth's magnetic field was not present. When we were first setting this up, and I'm not taking any part in this, I'm saying the collective we, but not myself. When we were first trying to get this set up, we asked some people to come in and give us a quote for how much would it be to actually create something like this. And they were like, oh yeah, so for magnetic fields this strong, you just need, for this large and this strong specifically, about $40,000. Because you'll need some active cooling because there's a lot of current and all this stuff like that. And we're like, wow, okay, $40,000. You said 1,000. Okay. But somebody came up with a really ingenious idea of what if we don't use massive wires that need active cooling? What if we just use ribbon cable? And now I know a lot of you guys probably haven't seen ribbon cable, but older computers used to use these bundles of wire, and it was like 20 wires all in a sheet together called ribbon cable because it's a ribbon of wires. But using these very, very, very tiny wires and getting like quite literally hundreds of turns by just wrapping this thing around a couple times, we were able to create that exact same dipole moment, but with a current that wasn't too hot and was sustainable by equipment that we already had in the lab. So there's some really cool effects that you can do with these things. And I bring up coils are very important because they're in literally everything you're using right now. If you're using a computer or a phone to watch me right now, so I'm assuming you're not like peering into my window seeing me do this thing, coils are in all of those. Wireless charging, coils, power adapters, coils, inductors of any sort, coils, speakers, coils, everything. There are so many different things that need to use coils because the magnetic field is incredibly useful for most of our electronic doings every single day. If we wanted to create some sort of massive synthetic field, I imagine that would cause some issues kind of all over the place. Turning it on would be actually the biggest scare because as long as everything is just fine, what we're going to find soon here, remember that it takes moving charges. It takes moving charges to actually create a magnetic field, and it's going to take moving charges to feel the force from a magnetic field. So the only place that this would actually be an issue is when you're actually turning it on. Once it was running, everything would be fine. We'll get into that one pretty soon here. Not quite today, though. But yeah, coils are in everything. There's all sorts of stuff that uses all of this technology all over the place. like quite literally all over the place. If you ever pick apart some electronics thing and you find that all of the wires are wrapped around each other, right? So they're braided together, that's to stop stray magnetic fields from causing issues inside of those wires and to stop them from producing magnetic fields themselves. So it's annoying, but it shows up everywhere. There's a lot of cool things in this one. So talking about these magnetic fields though, and all of these coils and trying to do things with them, let's talk about maybe solving some more complicated magnetic fields. So you might remember, working with electric fields, we started by talking about what creates electric fields. They were charges, and then we said, okay, well that's cool, but what if I wanted to do some three-dimensional shape? What if I wanted to do something a little bit more complicated? Do I really have to do this three-dimensional integral just to get a stupid sphere? And I said, well, yes, but also no. Because somebody very clever came up with this idea that you don't need to do that integral. Like we see an integral in here, but Gauss's law really told us that you can do complicated integrals with only geometry as long as you're in some specialized cases. And as long as you're in those specialized cases, you're golden. And we can kind of extrapolate that. Sometimes we can look at slightly more complicated cases and approximate things or anything like that, but this worked out very well, right? And this simplified a lot of very complicated problems so that they were suddenly solvable for us. Is there a similar thing for magnetic fields? And you should know by now, of course there is, right? They're the same force. They've got very similar things the entire time. But instead of Gauss's law, this is now Ampere's law. But, and it's also not using whole shapes anymore. Now we're actually just focused on loops, right? Which is all about this stuff, right? Loops for days. So here's Ampere's law. It's the same kind of deal. Let's imagine that we take some Amperian path or an Amperian loop, which is what we see in my dotted line here on the outside. If I were to take the magnetic field dotted with the path all the way around. So take the magnetic field, how much is it pointing in the direction of my loop, and how strong is it? And take that all the way around the loop. That would be exactly equal to mu naught times the current going through my loop. So it's a little bit different, but we can see there's a lot of similarities between these two. Now, there are a couple things that I do want to specify here. When we're talking about something like I through, we're specifically talking about a net current. So if we see I1 going to the right and I2 going to the left, then we need to take the difference between those two because they're counteracting each other. If I've got 5 amps going this way and 5 amps going this way, my net current going through is 0. So we have to keep that in mind. Anything to the outside, like I3 here, does not get counted. But you can imagine that this might be a little bit complicated at first. Of course, this can be a little bit complicated, and this shape is meaningless to us right now, but if we could find some slightly more symmetric cases, perhaps this would be very useful. Okay, so let's try this with a whiteboard problem. Let's imagine, and it's not drawing again. What is it doing? Oh, I have no idea. Let's imagine that I have this shape right here. I'm just going to erase those by hand for now. I don't know what's going on with this thing. I want to find what is the integral around this ellipse. And if we were in a class, then I would make this play and the green bar would descend all the way down and I would say very panicked words the entire time to really give you the sense of urgency. It's another very, very, very complicated problem that takes a very long integral around an ellipse to do. But there's a way out. What is this integral? I don't even want to mute myself or anything else. I want to just see if we can immediately kind of pull this thing out. What should this integral be? What do we think? All right, so for this one right here, I'm going to use Ampere's law. Ampere's law tells me that the integral around a closed loop of b dot ds is equal to mu naught times I through. So if it's mu naught times I through, then I'm going to look at this. I'm going to say, okay, we've got 8 amps coming out. We've got 6 amps going in. The difference, the net current going through, is 2 amps. So my final answer is just mu naught times 2. And that's it. All right. So, as I'm trying to hint towards here, just like Gauss's law was useful, well, not very useful, we could do it in a lot of cases, right? We could take any shape we wanted, no matter how ugly that shape was. We took our baked potato shape constantly. We had Pikachu. We had everything. Any closed shape, we could find the electric flux through that shape using Gauss's law. But it wasn't very useful for calculating electric fields, except in circumstances where we had a lot of symmetry. Same thing kind of goes on here, right? Ampere's law is so very useful. We could find this integral value for a lot of different things, but the integral value is not what we're after. We're after the magnetic field, B. So we have to look for these high symmetry cases. And a wire is a perfect case, right? Especially because we've already done this with a real integral. What if I actually take this thing? What if I draw my loop so it's centered on the circle like what I've got right here? In all cases, all the way around the circle, my magnetic field would be pointing directly along the same direction as S, right? And I'm trying to do this in a way that you guys can actually see it, but my hands can actually twist. So we know right off the bat, the dot product goes away, right? Because they're always aligned. All the way around the circle, they're always aligned. So the dot product goes away. And then we also say, okay, well, we are symmetrical in this entire case. So the magnitude of the magnetic field is also the same all the way around the circle. So B can come out. Then I am just taking the integral of ds. That is, how long is my path? It's all the way around a circle. It's 2 pi r. We take that, B times 2 pi r is equal to mu naught times I, and there we go. We have recreated There we go. We have recreated the magnetic field that we solved out for when we had done this thing using an actual integral. But now, without the actual integral, right? Let's be real. This was not an integral. This was geometry. So we can use this. We can kind of extrapolate this. We're no longer limited to one-dimensional, infinitely thin wires. We can actually look at more complicated cases as long as they still have some sort of symmetry that we can exploit. So, let me move myself back down here. Let's try to take a look at this. Let's imagine we have some realistic wire, so it's actually got some sort of thickness to it. First, I want you to redo these steps that I've just shown you. Right, we remember what happens with these things. When we have a three-dimensional object that can be approximated as 1D, we get the same answer when we actually take this thing. So you know what to expect for part A, but I want you to go through it anyways just to get familiar with steps. Then, for part B, here's where we get a little bit unique. Now we are looking inside the wire. What is the magnetic field inside of the wire? All right, let's start taking a look here. So I'm going to steal this picture, but we're actually going to draw our own cross-section of this as well. Let's get this thing pasted in there somewhere. Okay, so let's shrink it down just a little bit, because again, I'm not going to draw on this thing a ton. So first, more as an exercise just to go through, because we have seen this at this point. What if we take the circumstance where we are looking where R is greater than R? And if you're listening only, that is probably very confusing. But we imagine some sort of loop like that, right? That's larger, that encompasses the entire wire. In a case like that, then what we're expecting from our integral We're going to follow all of the same arguments that we just did in that example slide, but I'll talk through these one more time. Mu naught times I through. So first of all, in our I through, our loop goes all the way around the wire. So I through is just the I going through the wire, right? There's no other source of current. On top of that, because we are looking in the circumstance, we've got B dot ds. ds is going around the circle. We know the magnetic field wraps around as a circle. They're always pointed in the exact same direction, so the dot product can go away. So now we're left with B ds is equal to mu naught times just I, the I of the wire, okay? Well, now I know that because, again, I'm going around and it's symmetrical and all that good stuff, B is a constant. So it can be pulled outside of the integral. I'm left with ds around a closed loop or a circle times mu naught times I. Then we can say, okay, well, it's just the path around a circle. That's 2 pi r long. Solve this thing out, we find the exact answer that we expected to find from the very beginning. Mu naught I over 2 pi r. There's our first answer, and that should be no surprise at all. It's what we've already calculated out. Now, when we start to look at what's going on inside the wire, now we've got something that's a little bit more messy. So let's draw this thing out real quick. Let's imagine that we've got this wire. Let me take my cross-section of this thing, and I'm going to try and steal that color real quick to make this a little bit, I always lose my bucket. There we go. So now we're imagining the circumstance where we have only a part of it. We don't have the entire thing. Go ahead and label all these things out real quick. So we've got little r now, and we've got big R, and we're looking when r is less than r. What do we see? So now, again, everything that goes on the left side is all about what's going on with our Amperian loop, right? Just like with Gauss's law, it doesn't necessarily matter what's going on with the entire shape. This expression that we have is focused on what's going on with the loop that we have chosen. So that means when we go through with the integral side of things, well, over here, not much is going to change. Because where the loop is drawn, how that's evaluated, that's really no different. But what we see on mu naught times I through, here's where stuff gets a little bit wacky. Because we're going to completely discard anything that's happening out here. The easiest way that I imagine to do that, and let me go through the same step-by-step order here. The dot product goes away first. So that's what's going on the left side. But over on the right side, what we would see now is that mu naught times the current density times however much of the cross-sectional area we actually have, pi r squared. Right? That says let's take the current density of the entire wire and let's only focus on this spot. That's the only spot that we actually care about. So let me carry on with that, right? Let's just kind of leave that as is for another minute or two. I know my integral b ds is going to come out to be b times 2 pi r. Now, here's something that I run into. J is not some sort of value that I've already got defined. The only things I had when I started were I and capital R. So I need to put I or rather J in terms of those things. This entire wire, the entire thing has a current density given as I over pi capital R squared. Right? Because again, what's going on with J is something to do with the wire, not anything to do with our Amperian surface, or our Amperian loop, rather. J is something intrinsic to the wire itself. So we need to take that expression and plug that in down to where we've got going on down here. Let's move some things over. So I'm first going to solve this out. I'll plug in J as my last step here. B is equal to the pi cancels out. I've got mu naught J R over, anything else? Is that it? Over 2? Trying to make sure that I didn't miss anything. I think that's it. But now I need to plug in my expression for J. So mu naught I R over 2 pi capital R squared. And that's what we get for our final magnetic field. Inside the wire, at least, right? Outside the wire, it's our old expression. This kind of result should not come as any sort of surprise. We saw the exact same thing when we did this with the electric field, right? And in fact, let's plot this out and kind of prove the point. If we are talking about the magnetic field versus the radius away from the center, then what we expect to see here is a linear relationship as we build up more and more charge until we get to a breaking point where R is equal to capital R. Now there's no more wire, no more current to pick up as we make the loop bigger, and we go back to our 1 over R kind of description. And that's what we get. And that's the exact same thing that we saw when we were dealing with the electric field. So it's kind of comforting that we find it again here, like an old friend. And I'm sure we all consider it to be an old friend. B.ds, that is the integral of B with, that's always asking how much is the magnetic field going along the path that I've taken, right? So it's a dot product, so how much of the magnetic field is actually going around the loop versus going off in some other direction like this where the dot product would be less than maximized. So we do need to keep taking a look at a couple last things here because we do have just a couple more things to look at. So solenoids, which you have now seen in the lab, are essentially collections of a lot of different rings all put together. Here's the general idea, right? One ring of current gives us a nice consistent magnetic field and easy to work with. What if we stacked a bunch of those together? Right in the middle of the ring, the magnetic field goes, let me highlight this one, it goes like this, right? Where it's pointing directly through the middle of the ring. So if we were to stack a bunch of these rings together, then we would expect a very long single direction magnetic field. And this leads to a slightly interesting point. This is a little bit of a strange thing at first, because what goes on then with the outsides, not railguns yet. Not railguns yet. Soon railguns, but that's next time. What goes on with this is that on the outside, because of what's going on here, the magnetic field actually mostly cancels out. All of the different directions of magnetic field are going against each other, and they end up canceling out from all the different rings, but on the inside, they're all consistently flowing in the same direction. When they all stack together and you put them close enough together, you actually get, I know it's kind of hard to see, but it's a bunch of straight lines going all the way across in a uniform magnetic field. Now, this is incredibly useful, right? This is used for all sorts of things, just like what we talked about when we were talking about how an infinite plane is not a real thing, but large enough will create a very uniform electric field that we can assume is completely uniform. Just in the exact same way, we can use a solenoid to create a uniform magnetic field inside of the solenoid. Now, real solenoids don't just go in one direction because they have ends. And technically at the ends, they loop back out again, right? Just like we would expect. So it does form loops. In the infinite case, we would expect it to technically be zero magnetic field outside of it, but real solenoids just have a very, very weak magnetic field outside of them. But within a good approximation, it's negligible compared to the magnetic field on the inside of the wires. So, again, these are very, very important. We use coils in almost literally everything. They are constantly being used in all sorts of things, whether we realize it or not. There are coils everywhere. Your car would not run without coils. Your computer would not run without coils. Most of electricity would not run without coils. The power coming into your house uses coils. They're everywhere. So it's good to talk about them. And the way that we can do that, if we were to go through these derivations, what we would find is we have an expression that looks like this at the end of the day, but this one over here is actually pretty useful most of the time as well. They're both trying to say the same thing. If we were to take Ampere's law on a piece of this solenoid, and we were to look at the magnetic field, if there's no magnetic field along the top path, there is a magnetic field along the side paths, but the dot product means those are zero. The only part that actually matters is this part right here. So that's B times S, and nothing else, is equal to mu naught times the number of wires that we have with current going through them. So I bring up both of these things because technically for the infinitely long solenoid, you can't have an infinite number of turns and an infinite distance and come up with something reasonable. So instead we use what we call turn density, which is how many turns do you have in a meter? Now, if you have real solenoids that have length and a real number of turns, then this equation on the left is probably a little bit more useful for you, but really they're saying the exact same thing. So, I want to try this one in a problem. Let's imagine you are working maybe for some sort of educational physics lab and you need a solenoid for a demonstration, which is something that we actually have to do. Let's imagine that you need to create a 20 centimeter long solenoid that has a magnetic field strength of 5 millitesla, and you want this thing to be like nice and clean and consistent, so you're not going to double up any of the wires. They're going to look just like this, or just like this, where it's one wire stacked right next to the other one all the way across. You've got two options, two different wires that you might use to do this, and you look at the ratings of each one to say, okay, well, the 18 gauge wire can go up to 6 amps before it starts to burn and melt and do bad things. The 26 gauge, a little bit smaller, can only carry 1 amp, but because it's smaller, I can fit more turns on my solenoid. Which wire should you use? How much current do you need to put through that thing to make it work? I'm going to say let's start to take a look at this one. So I do want to steal this picture as well as I can. I know it's not grouped up, but I'd like to have the visual aid here just to kind of remind ourselves what we're looking at as we mess around with this thing. So we've got two different wires that we're going to need to deal with. And I'm going to just take these things in the order that I see them. So long story short, we know that in either case, no matter what we're looking at, the length of the solenoid as we would expect to see it. Could I have a working pen, please? Could I have a working pen, please? Nope. What about now? There we are. So we know that the length is supposed to be 20 centimeters of this solenoid. Right? The first question we have to ask then is, all right, well, how many turns can we actually fit on 20 centimeters? We're using wire 1, which is going to be our wire that has, let me go back to this thing, our wire that is our 18 gauge wire that has a diameter of 1.02 millimeters. And I add 18 gauge. So diameter 1.02 millimeters, or let me rewrite this into common terms. 0.00102 meters. Now, what I'm looking at here is I'm trying to stack all of the wires kind of like this, right? Where they're all a bunch of circles stacked end to end. So then, the total number of turns that I could fit on this thing would be the total length that I've got divided by how much length each wire takes up. Plug this stuff in all together, and what we end up finding is that for at least the 18 gauge wire, we could fit a total of 196 turns, 196 coils on this 20 centimeter long solenoid. Now I'm going to ask, okay, well, what is the maximum magnetic field that it could generate, right? Because we know we are looking for a specific magnetic field, but let's first make sure that we can actually even get there. Let's figure out what maximum we can hit, and then we can scale it down from there. So I'll take my solenoid equation, right? And before I mess it up, I'm going to take a look at this. I'm going to use the one that I've got over left here. Mu naught capital N, I, divided by, and that S for me is going to be L. Divided by L. So, plug in all these values. I'm going to say max, M for max, M for max. Hopefully that's large enough that you can see, but even if not, it's just a little tiny M. When I plug in all of these things together, I did number crunch this one earlier, what I find is a maximum magnetic field of 0.00741 Tesla. Or, whoops, I shouldn't write the M first. I should say 7.41 millitesla. So right off the bat, we know this one will work, right? That's our maximum magnetic field that we could create. We could go all the way up until this point before we'd start like lighting things on fire. Okay, so wire 1 definitely works. Let's check wire 2. Because ideally, I'd like to use the one that uses lower current, right? That would be nice. But let's figure out if we can. No worries. I was trying to figure out if I should say something about it or if I should just leave that one go. So the second wire is our 26 gauge. And it's got a much smaller diameter, right, of only 0.41 millimeters or 0.00041 meters. Okay? Then we plug it in the exact same way. How many turns could we possibly get on top of this thing? That would be 488 turns. And with almost, or more than, double the number of turns, we could end up having, you know, maybe a lot more of a stronger magnetic field, if only we have the current. But the current is limited, whereas current could have been, Imax in this case was 6 amps. In the case of the 26 gauge, Imax is now only 1 amp. So if we plug this into our equation over here, the maximum magnetic field that could be generated from our 26 gauge solenoid is actually going to only be 0.00307 Tesla, or only 3.07 millitesla. So that means wire 2 is out. There's no way that it could work. So then we know which wire we're going to use to make the solenoid. The last thing we need to do is tune this thing up so that it's got the right current. We know that the actual magnetic field that we want is 0.005 Tesla. So set it equal to mu naught N I over L. We have everything else. We just solve out for what is our final current that it needs to be to get this, and we should find 4.06 amps. And there we have it. Oh, I wanted that to be in purple, please. Thank you. All right. I think with that, we will close out 29-3. Next time, we have one more lecture on chapter 29 before we close it out for good here. But then we've only got 3 more lectures following this one. So at least 3 more on the books. I'll have a couple more for you guys as we get into those sometime towards the end. Some optional lectures of things that I think are just really cool and fun to talk about. But anyways, until next time.